research for gene therapy, but it can now be applied to gene drives. And as soon as we realized it could be used for gene drives, we realized just how easy it was and how, in principle, anybody with very elementary skills can make a gene drive. In fact, we even came up with a way that they could make them accidentally, just in the process. And then if they make it in a mobile organism, mobile in any sense, once you get down the drain or whatever, it could spread exponentially through the population. So our first papers on it were sort of detailed ways that it could go wrong, or you could reverse it, or and ways of maintaining safety. No experiments. So unlike some of the flu virus experiments, the first the public heard of it was fait accompli. And then now we published a paper. We did it in yeast in a very special way that made it so it couldn't escape even to breach the physical barriers. And the yeast experiment was extremely rewarding in the sense that it spread nearly 100%, almost undetectable non-spread, and in a variety of yeasts throughout the phylogenetic tree. Yeah. So when if all the stuff I read, the one that fascinated me most is trying to analyze the longevity of the bowhead whale. If you have an animal that the mammal, similar to us, that appears to live upwards of 200 years, and you're looking at that, and you think, well, how do you do that? So you can't wait 200 years to see if you're right. So how would you work on that problem when we're not going to be around 200 years to congratulate you on not being right or wrong? Yeah, my Department of General wasn't too happy about having a bowhead whale facility either. But I think that longevity is a kind of a crazy goal scientifically, in that because even short-lived organisms like worms and mice, you're talking about a payoff or an assay where just one turn of the design, build, test, learn cycle is longer than a graduate PhD. So what you want instead is not longevity, but aging reversal, where you're looking for signs of change that are fairly instantaneous in weeks rather than years or decades. And this is perfectly reasonable. I mean, you can do it in model organisms. My close colleague collaborator, Amy Wagers, did what's called heterochronic paramyosis, where you suture together a young and old mouse, their whole circulatory system, and you can find factors that contribute to the rejuvenation of multiple organ systems in the older mouse. And some of these have been followed up on in great detail, like GDF11 as an example of a protein that can circulate and has profound multiple consequences. So I think that's the way to approach it. Now, we not only worked on the bowhead whale, which was 200 years, but the naked mole rat, which is dramatically different from other rodents. And I think, as much as I champion personalized medicine, I will be the heretic, contrarian to myself in saying that the thing that's wrong with humans, for the most part, is that we're human. I guess there is anything wrong with us. That is to say, the reason that we can't plow through a meter of ice the way the bowhead whale does from under it, or live so long. And the reason we're not normally adults the size of a mouse is because it's human. It's not interpersonal variation in our genome. It is fundamental, and there are ways we can change that. Right. And what really makes us human, what we like to think makes us human, is our intelligence. And I understand you also want to mess with that. And now that let's be reasonable, artificial intelligence is getting a lot of attention lately, but as I understand your view is what is more immediate and more realistic is just slightly shifting our own intelligence. And something was a little bit against it, that this could be possible. Let's lower expectations a little bit and broaden the scope. I mean, we heard earlier about machine-human interfaces and how great it is that we can now get a microscope the size of the end of our pinky and optics is a great revolution. But the fact is that both electronics and optics are pathetic compared to biology in certain ways. In particular, the amount of code, the amount of digital information that you can pack into a biological polymer is on the order of 1 million times denser than any electronic components that we have. And the energy that is consumed in reading and writing to such a biological system is also about 1 million times better. And the cost curve or the performance curve for biology as technology, as Alicia will tell us, is not any slower than electronics, and some would argue it's a bit faster, in that when we started working on next-gen sequencing, the cost curve for electronics, which was a big part of next-gen sequencing, predicted 60 years, 6 decades, and instead it took about 6 or 7 years, okay? So we're ahead of Moore's Law, and we are going faster. I will submit for consideration. I wouldn't call this improving our intelligence necessarily, although I do feel quite a bit more intelligent when I'm connected to Google than when I'm not. But I think that we have serious problems to deal with that I've hardly listed before that require biological interfaces with information. And information may or may not be in a digital electronic computer, but it's information. So, and
In 2003, which intrigued me, where does it go? This is a very bold claim. We suggested the complete determination of a biological system is a concrete, achievable goal. And do you still feel that way?
There's a little more to the right context on that, but so first of all, yes, I think it is. The simple answer is yes. And by complete, we're talking about, and synthetic biology provides us with some way of saying that we can reconstruct a biological system. That doesn't mean it's full understanding. It means we can reconstruct it. We can also say that we don't necessarily need to have full understanding in order to do amazing things. I would submit that we do amazing things with vaccines since the 1700s without full understanding of the T cells, and cytokines until recently. So what I think we can get atomic level information. At this point, we have a new method called coincidence sequencing, which we did not exactly have in 2003. We had the idea in 1999, so that was in the back of our mind. But it allows you to essentially get the name of many of, if not all of the molecules and their two-dimensional coordinates. So I think we're on track for that kind of analysis. And synthetic biology will give us some feedback as to actually whether we can do the design, build, test, learn cycle on that complete analysis.
Right. One of the things you're working on is make faster models.
To really know that you understand all the parts, you can make something that's radically different. Ironically, if you make a mirror in a cell, then you really haven't made a copy. You've made something with fundamentally new properties, but you've shown sophistication in taking it apart and putting that together.
And how many people work in your group? To me, it's an important question. For how large?
Most pretty small. Yeah. So our group is not a production group in the sense there are much bigger groups like BGI which is a California Shenzhen, China collaborative. But you could consider that part of my group, right? Because I was one of the investigators of both companies before they merged. My formal group that I'm responsible for is 102 people in it, sort of equal graduate students, postdocs, and engineering staff. But I think, to innovate, you don't necessarily have to have the production completely integrated, although it helps. But you do have to integrate a large number of different disciplines. So that's why you end up with that kind of force.
And how do you decide to divide your time between, which I find impossible. I can't. If I'm working on several things, I waste half my time to try to divide my time. And you seem to have some sort of gift for that.
Gift for curse. But, I think there's only one project, so I don't have to divide my time. It's all one thing, as far as I can see.
You don't walk in the morning and there's just several different people.
Yeah, we take turns. And we have 6 speakers a week in lab meeting, and I meet with companies when I'm in town, like today, and take care of us all. Okay, so we were talking about building community. This is my community, groups that have helped get our technologies out into the world, and this is also my conflict of interest, so thank you slide. I thought we could take a moment of silent reflection on the loss of 100 centenarian genomes and $15 million for research, almost exactly a year from today, a year ago. If you want to know more about it, you can do a Google search of AGXP or X Prize for public debate. Time's up. But here's a star. We're going to comment just a few slides on epigenome analysis. We have an exciting new sequencing method, and then most of it's going to be on epigenome engineering. And you'll see why I think that's an interesting complement to most of what we'll be talking about here today. So first, epigenome analysis. In particular, analyzing the 3D disposition of RNAs within tissue samples, sections, so forth. We would really like to be able to read out what the genome is playing out in its epigenomic state at high resolution and with full comprehensiveness that we expect of RNA sequencing, for those of you who know that. So what we do is we take this little cube of tissue here, and where each dot is a single RNA or principal protein or DNA molecule, but for now RNA, and we make cDNA and then fluorescently sequence it, just like next-gen sequencing. In fact, this is one of the reasons that we developed next-gen sequencing back in the late 90s. And almost any fluorescent next-gen sequencing will work for this. You tended to use ligation, but the polymerase works as well. Now, this produces a very dense amount of information. Instead of having it normally when you do RNA analysis, you'll take the RNAs out of the tissue, you'll randomly distribute them on a slide, and you'll read them there. You've lost all the three-dimensional information. In this case, we just said, why not read them where they are? You get the quantitative information, same quantitative information by counting, but you also get the X, Y, and Z coordinates which are meaningful. You want to do this as high resolution as possible, so you maximize the number of RNA sequences you get per slide or per experiment. And also, it's a little crowded in there. So we have 4 methods that we have worked on that are all working well. One is spin sections. I think the first two are fairly obvious. Deconvolution is a computational method. Down below, it's on the slide, we say super resolution, which allows us to get down to 10 nanometers from 400, the kind of typical resolution. And what you can see here is just in white is the sort of typical resolution pixelated, so we've blown it up so you can actually see the pixels. That would be the resolution of this image. And then this little square here is blown up to show the resolution, we see super resolution. So when we say that it's 40 times high resolution, we really mean it. And this particular image was taken from Ting Wu, a professor at Harvard Medical School. Genetics. And that's one method of getting it, which is super resolution. But we can actually even read multiple RNAs in the same voxel, no matter how tiny that voxel is, no matter how high resolution, we can get more than one sequence from that. And we do this by a trick called molecular stratification. In this case, we'll read a subset of the messenger RNAs by selective priming and selective sequencing. And then we can go back and get a different subset by using a different set of primers. So for example, you can see here down at the bottom how much cleaner the signal is by getting a subset than it is by getting using random prime with all possible fixers. Here we take a subset which is reduced by 16-fold. So improvement in quality, and we still can get the same ultimate number of RNAs identified. And this is the last slide on this series, showing an example of one messenger RNA taken out from some of these fluorescent sequences, such as the one I showed in the previous slide. But looking at multiple reads that you obtain for this particular long messenger RNA, which is 8 kb long, which is fibronectin. This is a wound healing model system for using human fibroblasts. And so under here, on signal growth conditions, and along the x-axis is 8 kb transcript, and then there's a histogram showing the reads, individual single molecule RNA sequence reads that we identify matching with the transcriptome. And you see a little gap here, which could be that we were missing that data artifactually, or it could be that it's alternate splicing. It turned out it was the latter, because when we changed the media, and there's a variety of other experiments to show that this is a physiologically meaningful change from fetal dopamine serum to epidermal growth factor in the wound healing paradigm. We now have this alternative exon number 25 from fibronectin shows up in our in situ sequences. And remember, we're getting the 3D coordinates of this tissue as well as the quantitation. So that's all I'm going to say about epigenome analysis. It'll be clear that we use these and other tools when we're doing epigenome engineering. But I want you all to be thinking of questions, because hopefully this is going to leave time for questions again. We need cohorts for this sort of study, and we've got a terrific one that's completely open access. It's the only one in the world that we know of that allows integration of genomes, environment, and trait data. This has been adopted by a unique collaboration between us and also collaboration between NIST and the National Institute of Standard Technology and the Food and Drug Administration for shareable standards for genomes and for cells. And this cohort is also kind of a front runner for sharing the data for testing of genome interpretation, and it also figures into a wish for individuals participating in research studies as well as medicine in general to be able to download their own data that is now implemented by the U.S. government called Blue Button. Now, some people give up hope when they talk about multigenic traits or complex diseases, and of course, aging is the most multigenic trait of all, and we all have it. We all die from it, probably. But there's no reason to give up hope. I think that it depends on the tools you use. And the tools that have been focused on the most, I think, are inappropriate for certain things. They have their uses. For example, genome-wide association study, you might take a quantitative trait like height, and you get a nice bell curve, and you have cohort sizes that are gigantic, in this case up to 200,000 people, and you find 700 genes that impact maybe a millimeter each in height, and you say, how could we possibly, and each have variance and variation and environmental components, how could we possibly diagnose height from the genome, much less cure it? I'm sure you're wondering why I want to cure height, but anyway, the point is this is a kind of a bleeding edge example of a multigenic trait. And I would say that this is thinking about it the wrong way. The alternative to this multigenic approach, which is valuable, is looking at a very small number of individuals and a very small number of genes out at the tip of the bell curve, at both ends of the bell curve. There are very interesting things that happen out there, and what you find is that there can be a small number of genes, could be 1, could be 2 in this case, of growth hormone and growth hormone receptor, which explain so much, and they provide a therapeutic insight that you don't get from the 700 genes that give you a millimeter each. And I think this can be generalized to a variety of other interesting multigenic traits that are involved in age-related diseases. And I'm just throwing that out there as a hypothesis, and there are a few other examples other than this one. And the fact is that if you have a child who is delayed or destined to be short and given growth hormone, even after most of their colleagues have stopped growing at that age, they will continue to grow past the normal time and will achieve a nearly normal height. So this is episodic. That is, say, it overwhelms all those little effects of 700 genes that you get from studying the middle of the bell curve. The other aspect of this small cohort size that occurs out at the extreme, by definition, before not now, there's only one person on the planet that has this particular trait constellation. And so we call these N-of-1 studies. And it causes us to change from correlation, where we might need a cohort of 270,000, to focus on causality, which is better anyway. It's what we need to prove that we are there, and it also moves us towards therapeutic. And you can do causality with either human or animal tests. Here, 3 animal tests prove there was an N-of-1 of one individual, this 7-month-old, that had a myostatin double null, so it was missing both copies of the gene throughout his body, and the baby came out essentially looking like Arnold Schwarzenegger at his peak, but this was straight out of at birth without working out. Didn't reproduce in these 3 animals, but you can also do this in humans. And here's an example of something that we just recently published together with William Fu and Ted Parker's groups, where we had an N-of-1 cohort having a very early onset cardiomyopathy. And we could use normal cells, in fact skeletal cells from my own skin, to reprogram them both genetically, so they have missing one G that we thought might be causing the disease, so a one base deletion. We reprogram them genetically and epigenetically. We reprogram them to be a very well-ordered cardiac tissue, which then reproduces all 4 of the main traits: a little lipid disorder, the mitochondrial morphology, and movement, the cardiac beating. So one base, we prove that is necessary and sufficient for the syndrome, and is also presumably necessary and sufficient for fixing it. So the story that I'm kind of building here is that we need to embrace the outliers. The middle bell curve is great, but we really want to embrace outliers, and we want to be able to test N-of-1 studies genetically and epigenetically. We want to be able to engineer genomes. Now here are 4 of somewhere between 70 and 400 outliers who live past 110 years. I'm sure you're all aware of this. If you want more information, go to supercentenarianstudy.com, where we're well on our way to sequencing most of these individuals. And sequencing, we hope, I think that the statisticians would like to have them all have exactly the same gene change that would cause them all to live so long. I would like them to each have a different genetic change that we can prove in a causal sense and combine them in new combinations that we've never seen before. But biology will be what it will be. By the way, I'm not advocating smoking and drinking to excess or eating sweets. So embrace your outliers. It's rare, extreme. The rarer and the more extreme, the better. This is now not the outliers in the human species, which I was just talking about, but these are outliers that we found in a terrific database that if you haven't used already, I encourage you to take a look at it as well. I postdoc of mine, Pedro de Morales, who's now a professor at Liverpool, and now has expanded to over 4,000 species of animals with an animal aging database. And you can see these red diamonds are outliers ranging up to 400 years. And the question is, why do some humans live past 120 years, why do some animals live much longer than nearby animals in the phylogenetic tree? And so we have contributed with Pedro's group to the transcriptome and the genome of naked mole rat, and the bowhead whale will be coming out very soon for those of you who are interested. And we're looking for keys, genes, and gene variants that we can apply in causality studies. We have some examples of rare protected gene variants that I think are of interest in general and of interest to disease of aging. For example, we have alleles of APP, which, unlike most alleles of APP, which are either neutral or cause you to get early Alzheimer's, these alleles delay Alzheimer's by a considerable amount. They're considered a protective gene variant. Like everything on this list is protected. It's rare, fairly rare, and protected. It's not the most common allele. There are some that, from David Ulcher's group, is found that cause lower risk of type 2 diabetes, lower risk of coronary, 2 genes involved in coronary disease. And again, these are rare alleles in the population. I would like to sign up to get my genome changed to get these. And you've already seen myostatin and growth hormone LFT5 causes extra strong bones. Bones are almost unbreakable. This might be an anti-osteoporosis. But all these things will be, there may be some that are specifically involved in a more general mechanism of anti-aging, because we know that animals range from lifetimes of days to hundreds of years. 100 years. Now I'm just going to briefly show you some icons here. This was started by Hanahan and Weinberg. This kind of this idea of hallmarks of cancer and aging, with a half dozen, and then and usually also added, and Steve Ellis added another 5 having to do with stress and damage, which is kind of, as Mike said, is kind of a theme at this meeting. That's cancer, but you can see a lot of those are reflected again in aging hallmarks. There's some cases where proliferation works at odds against senescence, the senescence and corporate opposite, and some of them where they seem to be have common causes or common regulatory mechanisms aligned in the same direction. And finally, hallmarks are kind of analytic and telling you where we are, while the 7 sins, 7 deadly sins, are an effort to try to get at therapeutics that Okay, what I want to talk about is slightly different from all those. It overlaps in interesting ways, but it's about reversal. And not necessarily reversal of damage, but reversal of the epigenetic changes. I mean, there's no doubt that there is damage, and we need technologies for addressing them. And that can, but this is specifically about epigenetic changes. And here's the rationale. Wakayama and colleagues published this lovely paper in 2013, where they